Okay, so today we're going to go through the chapter 9, which is about momentum. So from chapter 9, we're going to learn something which is not very related to daily life. For example, momentum, impulse. So for these two concepts, momentum and impulse, we don't talk about them frequently in daily life, so it's like completely new concepts in physics course. So I think it will take you some time to get the idea of those concepts. So we will take it slowly. Now let's start from this chapter. So the first concept we're going to cover is the impulse. Now first, let's learn what is impulse. So for example, here we have a process or a motion of kicking a soccer ball. So these are three pictures which are taken at three different times. So the first picture happened when the foot has contact with a soccer ball. And then when the foot is moving, you will see in the second picture, that's the status of the maximum compression. You see, the shape of the ball is compressed. And at the end of this kicking process, you will see the contacts ended here. So after this moment, the ball will fly away. So that's a typical collision. A collision is a short duration interaction between two objects. So in this example, your two objects are the football and the foot. During a collision, it takes time to compress the object, and it takes time for the object to re-expand, as you see in this picture. The duration of a collision depends on the material. So when kicking this soccer ball, so first let me change my pointer into pen. Pen. Okay. So when kicking a soccer ball, the amount by which the ball is compressed is a measure of the magnitude of the force the foot exerts on the ball. For example, when the foot starts to contact or the contact begins between the foot and the soccer ball, you can see the shape of the ball is still spherical. That means the force is not big. So in this picture, in the second picture, if you see the shape of the football, it's being compressed. So when the ball is compressed, the magnitude of the force between the foot and the ball is bigger. And at the end, the ball is relaxed. In this situation, the force between the foot and the ball is not so big. So in this situation, the force is the biggest uh, force. So if you draw a picture of the force against the duration time, you will see at the beginning, when the contact begins, the force is zero. And then when the foot is moving on, it has more and more compression to the ball. You will see the force on the ball is getting bigger and bigger. And then when the ball is re-extended, you will see the force is getting less and less. And finally, at the last moment, the contact ends and the force becomes to zero. So if you draw this force against the duration time, you will see a curve like that. The force is applied only while the ball is in contact with the foot, and the impulse force is a large force exerted during a short interval time. So this is the impulse force, and we define a concept which is impulse based on such kind of phenomenon. Let's see. The effect of an impulsive force is proportional to the area under the force versus time curve, for example, which is shown here. The area is called the impulse, and we use letter J to represent the impulse of the force. Okay, so here is our definition of impulse. When the force happens, you can draw a picture of the force against the duration time, and the area under the curve is your impulse. So the area under both force curve is the same. For example, the above picture and the picture below, they have the same area. So both forces deliver the same impulse. If the area above and the area below has the same area, of course they have the same impulse. That's the definition of impulse. However, you can notice that in the picture above, that's a curve. In the picture below, that's a straight line. So that means they have same effort on the object, or they have the same impulse on the object. The area under the rectangle is F average times T. So this is a constant force, and this constant force has the same impulse, which is compared to the force above. So we call this force, this constant force, which can have the same impulse, to be the average force. Okay, now let's see a quick question. Two 1.0 kilogram stationary cue balls are struck by cue sticks. The cues exert force shown below. So which ball has a greater final speed? Or we can change the question to be which ball obtained greater impulse? Because in the future you will learn the ball gained, if the mass is the same for the balls, then the ball which gains greater impulse will have the greater final speed. So which impulse is big? The answer is the same. If you calculate the impulse, that's the area under the curve. If you do a calculation, you will see they are the same. It's useful to think of the collision in terms of average force. Average force is defined as a constant force that has the same duration time and the same area under the curve as the real force. So for this curve, its average force will be something like that. This is the average force, because under this average force, at the same duration time, they have the same impulse. So impulse J equals to area under the force curve, or equals to the area under the average force times the duration time, because if you do a calculation, they are the same. So impulse will have a unit of Newton times seconds. And Newton equals to, if you remember, 1 Newton equals to 1 kilogram meter per second squared. So Newton times second equals to this unit, kilogram times meter per second. So the later are the preferred unit for impulse. This one is preferred. The impulse is a vector quantity pointing in the same direction of the average force vector. So impulse, let's remember, impulse is vector. It has same direction as the average force. Okay, example 9. Finding the impulse on the bouncing ball. Okay, you can do it by yourself. This is calculation of the impulse. So when calculating the impulse, the only thing you need to do is calculating the area under the curve. So you should be able to do it. It's just a calculation of area for a triangle. Okay. Now let's see momentum and impulse momentum theorem. Intuitively, we know that giving a kick to the heavy object will change its velocity much less than giving the same kick to a lighter object. Then we can calculate how the final velocity is related to the initial velocity. Now, let's see. If you have an initial velocity and then you give a force to your object, so after the force exerted on your object for some time, or after an impulse exerted to your object, you will see your object will be moving with another velocity. So if we count initial and final velocity in this process, you will find the final velocity is greater. And we will learn how to do the calculation between initial and final velocity, and what's the relationship between initial final velocity and your impulse. From Newton's second law, the average of acceleration of object during the time of the force is being applied is, so the average acceleration equals to average force over m. This is Newton's second law. Do you remember that? F equals to ma, or a equals to F over m. The average acceleration is related to the change in the velocity. So we can write the average acceleration to be delta v over delta t. So that's the definition of acceleration. Delta v, of course, equals to v final subtracted by v initial. And then you can combine these two equations. So you will have F average over m equals to Vf subtracted by Vi over delta t. Then if you move delta t here and move m on the right side, or if you are not familiar with this operation, what you can think about is multiply m times delta t to both sides of the equation. You will get delta t f average, and then on the right side you will have m times v final subtracted by vi, which is here. Then you can rearrange the equation and you get this equation. And momentum, so here, first, what's that? Do you remember? That's impulse, force times duration time. And then we can define the momentum to be the product of object's mass and velocity, which is here, that's the final momentum, and here, that's the initial momentum. It has unit of kilogram times meters per second. So this is the same unit to impulse unit. Do you remember the unit of impulse? It's the same. And we define this is the momentum. Momentum of an object of mass is defined as mv, and momentum is p. Usually we use p stand for momentum. And then momentum is also a vector. And this vector has the same direction as the velocity. So, for example, if this is the direction of velocity, then the momentum of the object will be in the same direction. And this momentum, so any momentum could be decomposed into two components, x components and y components. The magnitude of an object's momentum is simply the product of object's mass and speed. Okay, so here are some common examples of some momentum. Now, for example, a falling raindrop. So the mass of falling raindrop is 2 times 10 to negative 5 kilogram. The speed is usually meters per second. So usually it's not going to be uh, much faster than this value. Do you remember why? It's called the terminal speed. Do you still remember the terminal speed we learned in chapter, which chapter? Chapter 4 or 5? Due to the dragon force. So anything dropped from the high enough position will finally get a terminal speed. For a raindrop, the terminal speed is 5 meters per second. So you can calculate the momentum. It's 10 to negative 4. So that's the momentum. For a raindrop, for a bullet, the momentum is about 2 kilogram times meters per second. And for a car on highway, you will see the momentum is a huge number. So that's just a list of some typical momenta. And now let's see the impulse momentum theory, which is the most important theory we're going to learn in this chapter. If you completely understand this theorem, then you're done for this chapter. Now let's see what's that. So the impulse and the momentum are related as the impulse equals to the change of momentum. Final momentum subtracted by initial momentum, or the change of momentum. So the impulse momentum theorem states that an impulse delivered to an object causes the object's momentum to change. Or in this equation, the change of momentum is your impulse. Because momentum and impulse are all vectors, so you can write this equation in x direction and y direction. So let's see some examples. So a potter delivers an impulse to a golf ball, changing its momentum. For example, at the beginning, the momentum of the golf ball is 0 because the initial velocity for this golf ball is 0. When the potter delivers some forces on the golf ball and it has some duration time, so it has an impulse. After this impulse, the momentum of the golf ball is changed. So it has some momentum moving to the right direction. And the change of the momentum is the impulse. So another example is when a soccer player delivers the impulse to a soccer ball. Okay, so here the initial momentum of the soccer ball is going down and left, and the soccer player uses his head to give some impulse on the soccer ball, and then the final momentum of the soccer ball changes the direction into this direction. So the change of the momentum of the soccer ball is an impulse from the head of the player. Okay, now let's see a quick question. A 2 kilogram object moving to the right with speed 0.5 meters per second experience the force shown. What are the object's speed and direction after the force ends? Okay, so initial speed of the ball is 0.5 meters per second. And then it undergoes some impulse. So first, can we calculate the impulse? Yes, J equals to what? F times delta T, or the area under the curve. this area. It's easy to calculate. Um, it's a rectangle, so length times height. Height is 2, length is 1/2, so the area is 1 kilogram times meter per second. That's your impulse. And the impulse is positive, means to the right direction. And then impulse equals to P final subtracted by P initial. Now we know the V initial, then we can calculate the P initial. So J equals to M V final subtracted by M V initial, because MV final is P final, MV initial is P initial. J is calculated here, 1 kilogram meters per second. So you know M is 2, you know V initial is 0.5. Can you calculate V final? Yes, so you can calculate it. So the answer is 1. Okay, so here's another example. You can try to do it by yourself. Now let's see another example, calculating the change in momentum. A ball of a mass of m equal to 0.25 kilogram rolling to the right at initial speed and then strike a wall and rebound to the left at another speed. So what's the change in the ball's momentum? And what's the impulse delivered to the wall? Delivered to it by the wall. Okay, so first let's calculate the change in the ball's momentum, delta P. So how to calculate delta P? Of course, P final subtracted by P initial. How to calculate P final? Of course, M V final is a P final subtracted by M V initial. So you know M, you know V final, you know V initial. So you can calculate it. So V final is negative 1.1 meters per second. V initial is 1.3. M is 0.25. So you can calculate delta P. That's the first question. Second question, what's the impulse delivered to the wall? J equals to delta P. So the impulse delivered to the wall, delivered to it by the wall, is the same as the change of momentum. So the two questions has the same answer. Okay, so here's more detailed calculation. Calculate P initial, P final, then P final subtracted by P initial, you get the delta P. Delta P is the same as J, so you have the same answer. Okay, so even though momentum and impulse, they're completely new concepts, but actually the equation for them is very simple. So in the calculations, usually it's not difficult if you remember the equations for them. The impulse momentum theorem tells us that the impulse equals the change of momentum. Okay. So let's see. If we want to stop something, let's see. If we want to stop something, that means P final equals to 0. Then the impulse should be negative Pi, or negative initial momentum. And average force equals to negative P initial over delta T. That means the average force needed to stop an object is inversely proportional to the duration of the collision. It's proportional to the momentum, and it's inversely proportional to the duration time. So if the duration of the collision can be increased, if the duration or the delta t of the collision can be increased, the force of the impact will be decreased. So that's why, for example, when you jump from a high position, usually you need to bend your knees to kind of make some buffer. Because when you bend your knees, the duration of the force between your leg and the ground becomes longer. So um, you have a longer delta t, then the force becomes smaller. So the same thing for the hedgehog. So when hedgehog falls from the tree, um, it simply rolls itself into a ball before it lands. The six spines cushion the cushions the blow by increasing the time or the duration time. Then um, the force, the average force to stop the hedgehog becomes smaller. So the same thing. When delta t is increased, the average force is decreased. So the animals are smart. So they use their techniques to protect themselves. Um, so so do people. So when we jump from a high position, we also bend our knees, right, to protect ourselves. We don't keep our legs straight because that will hurt our legs and body. Okay, here are some quick check examples. You can do it by yourself. Okay, now we have learned the impulse momentum theorem for object. And let's extend the impulse momentum theory from one object to multiple objects or a system. If there is a system of particles moving, then the system as a whole has overall momentum. For example, if you have three spheres, each of them has momentum, so you see they're in different directions. The total momentum of a system of particles is the vector sum of momenta of individual particles. P equals to P1 plus P2 plus P3. So if you sum them all in the vector sum, then the total momentum is the sum of the momentum in all the particles in the total system. And um, now let's solve some impulse and momentum problems. So first, a 150 baseball is thrown with a speed of 20 meters per second. And then it hit straight backward the pitcher at the speed of 40 meters per second. The impulse force of the bat on the ball has a shape shown here. What's the maximum force that bat exerts on the ball? And what's the average force that bats exert on the ball? Okay, so we have two questions. So we're calculating the force. Okay, we can use the momentum impulse theory. So first of all, can we calculate the change of momentum? The answer is yes. Change of momentum equals to final momentum subtracted by initial momentum, which is m v final subtracted by m v initial. Do you know what is v final? It's here. What is v initial? It's there. But please notice that um, it's backward when it's 40 meters per second. So it's negative 40 as the final. And do you know what's the mass? It's 150 gram or 0.15 kilogram. So you can calculate delta P. If you have delta P, then you know the J because J equals delta P. And J also equals to F average um, times delta t. And you know delta t is 0.6 millimeter, means 0.0006 seconds. So you know delta t, so you can calculate the average force. It also equals to the area of the triangle, which is 1/2 base times height. Base is 0.0006 seconds times the height. What is height? F max. F max. So in this equation, you can calculate F max. So you solve the maximum force and average force in this way. Okay, so you can see the details here with figures, everything. Okay, and you will get the final answer. The impulse approximation states that we can ignore the small forces that act during the brief time of the impulsive force. We consider only the momenta and velocities immediately before and immediately after the collisions. Okay, now let's see this one, this example. The car's change of momentum p is what? So can you calculate it? What's the initial momentum? Negative 2 times 10 because it's moving to the left. What's the final? 1 times 10. So what's the change? It should be 30. Okay, conservation of momentum. The forces acting on two bonds during a collision form an action or reaction pair. They have equal magnitude but opposite directions. This is what we have learned from Newton's third law. Do you remember that? Action reaction pairs. If the momentum of a bond 1 increase, the momentum of bond 2 will decrease by the same amount. For example, after when bond 1 and bond 2 have a collision, after the collision, their momentum changes. And the momentum decreased of bond 1 is the same as momentum increased on bond 2. That's the conservation of momentum. There's no change in the total momentum of the system, no matter how complicated the forces are between the particles. For example, if you have multiple particles in the system, uh, between each particles there might be some forces. However, the total momentum of the system is conserved if the interactions are just interactions between a pair of particles or among different particles in the system. So if there's no external forces, then the momentum of the system is conserved. That's the conservation of momentum. Internal force act only between particles within a system. The total momentum of a system subjected to only internal forces is conserved. So that's the law of momentum theory, conservation of momentum. Okay, you're awake in the night to find your living room is on fire. Okay, that's not good. Um, you you have one chance to save yourself, to throw something that will hit the back of your bedroom door and close it, giving you a few seconds to escape out of the window. You happen to have both a sticky ball of clay and super bouncy ball next to your bed. They have the same size and same mass. You have only time to throw one, so which one is better? So your life depends on making the right choice. That's an extreme example, but I'll give you the answer. The Super Bowl, because it will have larger delta P, which generate more impulse to the door. Why? Because now let's see. If you have a super ball, you throw it with the initial velocity, that's V initial, and then after hitting the door, it will come back, right? That's your V final. That's the change of V initial to V final. However, if you select the other ball, the ball of clay, then that's your initial velocity, and it will go with the door. So it has a final velocity like that. So which one changed the velocity more significant? Of course, in the first situation. The change of velocity is bigger, so the change of the momentum is bigger. So you have a bigger momentum change, so you will generate a bigger momentum on the door, because um, if you take the door and the ball as a system, if your momentum change to the ball is like that, delta P, then the momentum change on the door is like that, delta P door. This delta P ball. So bigger change of your ball result in a bigger change in the door, because the um, total momentum is the same. If your change of the momentum of your ball is very small, then the change of your momentum of the door is also very small. Okay, a mosquito and a truck have a head-on collision. Which has a larger change of momentum? Actually, the answer is the same. Okay, now let's see what are external forces. External forces are forces agent outside the system. For example, um, this is an external force. This is another external force. That's another external force. External force can change the momentum of the system. The change in the total momentum is delta P equals to delta P1 plus delta P2 plus delta P3. Or the change of the total momentum equals the change of the first momentum, the first object's momentum plus the change of the second object's momentum plus the third object's momentum change. So F net is net force due to external force. So the total change of momentum equals to the sum of individual momentum changes, and delta P1 equals to F exerted on 1 delta T, F exerted on 2 delta T plus 3, or the force on 1, the force on 2, the force on 3, delta T, or net force times delta T, because all of the three, it's net force. If net force is 0, the total momentum P of the system does not change. Or an isolated system is a system with no external force acting on it, leaving the momentum unchanged, which is the situation shown here. If there's no external forces, then the total momentum is the same, it doesn't change. If there are some external forces, then the momentum change um, of the total momentum in the system is the net force times delta T. The law of conservation of momentum states that the total momentum P of an isolated system is constant. Interactions within the system do not change the system's total momentum, or P final equals to P initial. The total momentum after an interaction is equal to the total momentum before the interaction. That's the law of conservation of momentum. Remember that the condition for the law of conservation of momentum is that if a system is an isolated system, or there's no external force, or the external force is zero. Okay, and momentum is vector, so we can write the same equation into x component and y component. Now, let's see. Here's an example. Two ice skaters, Sandra and David, stand facing each other on frictionless ice. Sandra has a mass of 45 kg, David has mass of 80 kg. Then they push off from each other. After the push, Sandra moves off at a speed of 2.2. What is David's speed? Okay, if we take Sandra and David as a system, is there any uh, external forces? Yes, there are some external forces. It's the weight and normal force for each of them. Weight and normal force. But the weight and normal force, they balance each other. So the net force of the system is zero. So this system is isolated system. So the momentum of the isolated system doesn't change. Okay, now let's see the initial states and final states. In initial states, they have zero speed. Then the initial momentum for the whole system is zero. So after a push-off, the push-off force is internal force. There's no external force. If there's no external force, this is an isolated system. Then the total momentum should keep the same. It should be zero too. So in this case, P doesn't change. P final equals to P initial equals to zero. If P final equals to zero, then P final equals to P, let's say, David plus P Sandra equals to zero. P David is M David V David. P Sandra is M Sandra V Sandra equals to zero. You know MD, MS, that's their mass here. You know the speed of Sandra, which is 2.2. So can you calculate V of David? It's very simple. So you can get the number, which is negative 1.2 because they're in opposite direction. Okay, so that's the example of using the law of conservation of momentum. Now let's see another concept, explosion. An explosion is when the particles of the system moving apart after a brief, intense interaction. An explosion is opposite of a collision. The force are internal force, and if the system is isolated, the total momentum is conserved too. For example, this is a rocket. When the rocket is pushing, let's say, the fuel on board down, then the rocket will be pushed up. So that's an explosion. And their total momentum should be not changed because if we don't consider the external force, if we only consider the internal force, then the P final uh, or the change of the momentum is zero. Okay, so that's the explosion. So here's another quick question. You can do it by yourself. Now, let's do one example together. A 30-gram ball is fired from 1.2 kilogram spring-loaded toy rifle, which is shown here, with a speed of 15 meters per second. What's the recoil speed of the rifle? Okay. Now, um, let's see the initial and final states. In initial states, the velocity of the rifle is zero, and for the ball, the velocity is also zero. If we take the ball and the rifle as our system, then the initial momentum is zero because the initial velocity for the ball and the rifle are all zero. So after the fire, the ball gained some momentum or velocity, which is shown here. And we are trying to find out the velocity of the rifle. That's very similar to a push between Sandra and Davy. Initial momentum zero, final momentum should also be zero because there is no external forces. Then we use the same thing. Um, P final equals P initial equals to zero. P final is P rifle plus P ball equals to zero. P rifle is M rifle times V rifle, and P ball is M, the mass of the ball, times velocity of the ball equals to zero. So you know M of the rifle and mass of the ball. You also know the speed um, of the ball. So can you calculate speed of the rifle? The answer is yes. It's very easy. So you will get the answer. So we don't talk about it for too long time. Now, let's see another concept, which is inelastic collisions. A perfect inelastic collision is a collision in which two objects stick together and move with a common final velocity. For example, you have an object 1, object 2, they have a collision, and then they stick together and they have the common velocity. Examples of perfect inelastic collision include clay hitting the floor or a bullet embedded itself in the wood, or two bonds hit each other and then they stick to each other. That's inelastic collision. The two boxes are sliding along a frictionless surface. They collide and stick together. Afterward, the velocity of the two boxes is what? Can you do the calculation? So the key is still the law of conservation of momentum. You need to remember delta P doesn't change. Delta P is zero. You can calculate the initial momentum of object 1 plus object 2. And then their final momentum is the same, but their final velocity becomes a common velocity. Then you can calculate the final velocity. Let's see one example together here. For example, two trains from several railroad cars. Okay, so two cars. There are two cars of trains from two directions with different masses are rowed toward each other. When they meet, they couple and stick together. The lighter car has an initial speed of 1.5. The collision reverses the direction at 0.25. What's the initial speed of the heavier car? Now let's see the picture. Before they hit, after they hit. Before, you know the mass of the first car and mass of the second car. You know the initial velocity of the first car. After that, you know the final velocity of car 1 and car 2 because they will have the same velocity. And you know the mass. Now, let's use the law of conservation of momentum. Delta P, in this example, delta P equals to 0 means P initial equals to P final. So P initial is M1 V initial 1 plus M2 V initial 2. So M1, 2.0, which is shown here. M2, which is shown here. V initial 1, it's here, 1.5 meters per second. V initial 2, it's unknown. Let's keep it as unknown. That's the P initial. Now let's see P final. P final equals to V final times M1 plus M2 because at the end they have the same velocity. They becomes like one object. So the total final momentum equals to the final velocity, which is shown here, times final mass, which is M1 plus M2. So the only thing you don't know is V initial 2. All the other numbers, you already know the answer. So you can do a calculation, then you get V initial 2. So that's the way of solving such a problem. You will get the answer to be negative 1.1. Okay. Momentum and collisions in 2 dimensions. So far we have learned or do some examples in 1 dimensions. It can be easily extended into 2-dimensional calculations. So the only thing you need to remember is when the motion of the collision occurs in 2 dimensions, we can solve it in each component, in x component and y components. In these collisions, the individual momenta can change, but the total momenta doesn't. Okay, so angular momentum, it's optional. If you are interested, you can read the angular momenta. Otherwise, it's not our focus. It won't be in your final exams. So we're not going to talk about angular momenta. Okay, so that's everything for this course, for this lecture. Um, this is completely new concept, which is momentum. And in order to learn momentum, you also have to know impulse and momentum impulse theorem. So this is a new concept. So please do the exercise after you learn this chapter. So please read the book, read the slides, try to do all the examples in the slides, and then finish your homework or assignments for chapter 9. Okay, that's all for chapter 9. I'll see you in chapter 10.